Okay, hello, it's Mr. Posh here in Studio M, and I'm here today to talk about the physics of music. So let's start with a quick review of the physics we already know. First of all, we know that sound is a wave, and we know that it's a longitudinal wave. So that means it consists of alternating compression and stretching of air. So for instance, if I took this plate and I pushed it really hard towards you, you might feel a little bit of air compression. Or if I pulled it this way, you might sense later a little bit of stretching of the air. But it doesn't really work very well in slow motion like that. If I could move this, say, like 1,000 times a second, you would perceive that as sound. And even though I can't move the plate that way, I can make a sound that will sound something like 1,000 cycles per second. So let me try that. So what I'm doing there is I'm simply whistling, and we can measure that later. We'll see if that was about 1,000 cycles per second, and we'll compare that to some other instruments doing the same thing. So that's all about sound. I think the other thing we already know is probably worth mentioning is that frequency is the rate of change of the vibrations. So if I'm going in and out with making my sound for 1,000 cycles per second, we would say the frequency is 1,000 cycles per second or 1,000 hertz. And musicians call this attribute pitch. So we hear the number of vibrations and associate that with a certain pitch. They get names in music like A, B, C, D, E, F, G, and there's more to it beyond that, which would get us into music theory. So let's see what, kind of a low pitch and a higher pitch sounds like. Here's a C note, very low. And then here's another C note. Let me take a nice high one. Ooh, not exactly in tune, this piano, but we're close. So you might be wondering too why there's a bunch of things named C on the piano. I guess it's just like Westford Academy blocks. They go A, B, C, D, E, F, G, and then they start all over again. So again, more on music theory we can get to and why that is. But for now, I think I'd like to get back to the physics. Got to go get a prop, and I'll be right back. Well, okay, I am back with my bottle of Stewart's Black Cherry soda. It's delicious. What I can do is make a whistling sound out of this, and we're going to hear a natural frequency. So this volume of air and this air column creates a kind of natural frequency, just like my lips did when I whistled a minute ago. And that is kind of the basis of how a lot of musical instruments work, believe it or not. And what you can do is change the amount of air to get a different note. So here is, and here's another one with a little bit, you can see, I hope that there's less in there. So those are two different sizes of air volumes, and that is how the different notes are made. So we've seen other examples of natural frequency too in class. We saw mass on a spring that wanted to go very predictably at a certain frequency, and now we've seen these two bottles do the same thing. Going to add one more bit of review before we dive into the music, because I think it's going to help us. There's two different kinds of, or there are many different kinds of modes where we can get a standing wave. And I'll just show you two of them here. You might remember when we did our springs on the floor experiment, we made a mode that looked like this, that had a note on both ends of the long skinny spring. We had another mode that vibrated something like this with two antinodes in it, and three, as shown in red, 3 notes, right? And then there were more. So those are called modes, even though we haven't called them that. We'll do that today. And what you get is the lowest possible frequency. That's the longest wavelength, of course. You get that if you use the entire length of the spring to just make a half a wavelength. And we call that the fundamental. After that, they go higher and higher and higher frequency. And there are just other things that can get added. What's interesting is that musical instruments in real life will vibrate in this mode, plus other modes, all at the same time. And the mixture of modes and how much of each one you get and how loud each one of them is, that gives you the characteristic sound of the instrument, or we would call that timbre maybe in music. And it's what makes a bottle sound different than a piano. So this will sound substantially different. Let me take the lower note. And let me see if I can find that note on the piano. And I'm going to play those one more time. We'll analyze those later in waveforms. That was a C note. This is pretty close. By accident. That's just where I happen to fill it. So you can see that those two instruments, and certainly others that you've heard before, will have different characteristic sounds that you could hear a recording of it and say, oh yeah, that's a piano, or that sounds like an organ or a clarinet. And so we'll be looking at that as we go here today too. So let's launch into the music now. I'm going to get another prop and I will be right back. All right, I'm back. Hey, truth be told, I just wanted to go get a sip of that Stewart's Black Cherry soda. All right, so let's see. That brings us to air columns, which are one of the main categories of instruments, where we take a column of air and we make it squeeze and stretch, and we vibrate it, and we find modes and standing waves inside of it, and it makes sound. So examples of those kinds of instruments are the flute, the clarinet, the Stewart's Black Cherry soda bottle. Any of those are really just vibrating columns of air, perhaps with a little extra volume attached to it. So that's the main principle of how that works. Now, it's a little bit inconvenient in a concert to be drinking your Stewart's and changing the pitch by adding and subtracting fluid. It wouldn't work very well. So that's why this slide whistle helps out. I can change, you can't see it here, but there's a plunger. I can slide this, kind of like a bicycle pump. There's a plunger that slides up inside it. And from that, I can change the volume of air inside this cylinder. So long length or long wavelength, lots of volume of air. And then I make it shorter. I should hear a higher note. Yep. And if I just do it back and forth, it sounds like the cartoons. So that's one of my favorite instruments. I also have this toy flute that makes sound. It's not the most beautiful sound, but I like it because it demonstrates the idea of changing the length of a tube. So if I press down on all of the holes, which I just did, I think I showed you there were holes all over the place. So I plugged them all up. The length of this tube is the whole length of the toy, right? Pretty much. And if I play it, I get one note. And if I do this, I effectively change the length of the thing. The bottom bit past the hole doesn't matter anymore. And I pretty much told the flute I want an anti-note here at the hole. So let's see if that changes the pitch. And there's more. I'm not an expert at playing this instrument, but the point is that as I make the tube effectively shorter and shorter by revealing more holes, I get a higher and higher pitch because it's a shorter wavelength. And you remember frequency is inversely proportional to wavelength, so that's why that's true. All right, so if we took this thing and had a few design improvements on it, we would have a real instrument. That would be, say, like a clarinet. And so I think what we're going to do now is we will have Christine demonstrate the clarinet for us.
All right, so I'm going to tell you about how to play the clarinet a little bit. And so basically you hold your right thumb underneath this thumb holder right here, so like that, and then your left hand goes just right here, and so you're basically holding it like you're holding a can of soup or something, so like this. And to control pitch, you're basically changing your mouth shape. So if you want to make it like sharper, you have to kind of tighten up your muscles. And to change dynamics, you basically just blow harder, and then to make it softer, you kind of pull back on the air, and yeah. So right now I'm going to play you a little piece, or an excerpt of a song that we did this past year.
Thank you, Christine. And hey, notice how Christine changes the pitch by either uncovering holes or by adjusting the airflow and the shape of that airflow in the mouthpiece. Inside the mouthpiece, there's a flap. It's called a reed, and it vibrates maybe something like this ruler would vibrate, bending back and forth like this at a sound kind of frequency. And that reed helps to make is part of making this sound. There's a lot of stuff going on in the mouthpiece that maybe would be beyond the scope of what we're talking about. So let's leave it at that, and let's have Liam pick up the story from here.
Hello, I'm Liam. I play the clarinet. You play with air and a reed. So brass instruments use like buzzing lips, but this is a woodwind, and I use plastic reed. Normally they're wood. So you put air into it, vibrates the reed, creates a bunch of noise that goes down all the way out into the bell, makes a bunch of noise. You control the pitch by aiming the air up, aiming it down. So in the mouthpiece, the mouthpieces are like really geniusly made. I don't know, there's a bunch of intricacies about them. But the direction you send the air, up or down, controls the pitch, as well as your fingers covering holes. And then for volume, it's the volume of air you put into it, the quantity of air. So I'll demonstrate now. So that's me changing the direction of the air, and then the volume. And a quick piece. So yeah, pretty simple. Been playing it since the 4th grade. It's a fun instrument.
Okay, so a clarinet uses a column of air to make sound. There's other ways to do this too. So string instruments use a completely different principle, and it's a lot like what we were seeing in class. You might remember that we noticed and actually experimented with mediums that had a characteristic, well, as any medium would, a characteristic speed for the wave. Let's see, help me out, Jay, Alex. So here, Jay and Alex are showing us how a wave medium, in this case a long skinny spring, can support a pulse traveling. And if you can measure the wave speed through that, you can just know the characteristic wave speed of that medium. Theirs looks to be about maybe 1 meter per second or so. And different strings would have different characteristic speeds. That is entirely the principle behind stringed instruments. Let's have Richa show us how.
Hi, I'm Richa, and this is my acoustic guitar. So to hold the guitar, I rest the body of the guitar on one leg, and then I use my left hand to press down on the strings and my right hand to strum or pluck the guitar. And to control the pitch of the guitar, I can use these tuning pegs here, and I can sort of tighten or loosen the string, and that'll kind of change the pitch of the string itself. And then I can also use my fingers and press down on the guitar strings, and I get a different pitch from each string, and that helps me form chords. And to control the dynamic or the volume of the guitar, I can either use my hand to strum, which kind of gives a little bit of a softer sound, or I can use a pick to strum, which is a little bit of a louder sound. And depending on the amount of pressure I put, or if I strum harder, then the sound will be louder. And finally, this is just a quick demo of me playing the guitar.
You'll notice that Richa changed the pitch in two different ways. One was by changing the length, by pressing down on things, and also by the tuning pegs, which change the tension and thereby change the pitch again. You might remember that V equals F lambda, so if you're looking for an F in particular that you have in mind, you can control either V or lambda, and that's what Richa showed us. Now, one last way to control V besides the tension is the mass per unit length. Those are the two things that determine the velocity or the wave speed going through the medium. So how would you change mass per unit length? You'd have to actually design the string to be heavier. Alpana is going to show us that on her ukulele and might even play a little tune for us.
Hey everyone, my name is Alpana and this is a ukulele. It's a 4-stringed instrument and it's got different thicknesses to the different strings to change the pitch. So that's one way you can control pitch by plucking each of the strings. Another way you can do it is this is a capo. It changes the key that your instrument is in. So you put it across the fret like that. It changes the key. And the obvious way to play it is with pushing down in the intervals between the frets. So that changes the pitch. And you use different patterns to change what chords you're playing as well. So there are almost two different styles of playing it. So this is a finger style. So that's called finger style. And then there's strumming. So this is an excerpt from an Elvis song. Wise men say only fools rush in, for I can't help falling in love with you. And that's the ukulele.
That sounded great. So as you can see, and as you can hear, our voices make really nice musical instruments. So let's see. So far we've been on strings and we've been looking at plucking and strumming as a way to get things going. We can also use a bow. You may have seen these in classical music. Here's an example of a bow. This one I use this with my bass sometimes, my acoustic bass, which I will not demonstrate today, but I'm here to show you the bow. And what it is, it's nothing but a bunch of strings of horsehair. These are literally made out of horsehair. And they're designed so that you can put grippy stuff on it. That's called rosin. I have a big tub of it here. It's kind of hard and could be a little sticky. You rub it on to make the thing a little bit grippy. And then that bow gets rubbed across a string. So if this pencil were a string, I would rub the bow like that, like that. And what happens is, as you pull the bow across it, it'll alternately grips and then slips, and then grips and slips, and grips and slips. And that adds energy to the string and gets it vibrating. Let's see, we've got Ivan up next. Ivan is going to show us how the bow works using his violin.
Hello, my name is Ivan, and I play the violin, which is a stringed instrument that you play by using a bow, which you then pull across the strings. To change the pitch while playing the violin, you will use your fingers on your left hand to press on the strings, which then changes the pitch. To change the dynamics while playing the violin, you will use your bow hand to then press harder or softer to change the dynamics accordingly. Here's a short demonstration.
Thank you, Ivan. That sounds wonderful. All right, so we have seen ways to add energy to strings. We have seen plucking and strumming and bowing, and well, there's no reason why we couldn't just hit it with a hammer. That would work too. That would give us lots of energy. It probably wouldn't be good for a delicate device like my bass, but it is something that is used in the piano. So inside the piano, we have hammers, and the hammers are covered with felt. They're a little bit softer than my hammer, and they're each attached to, not attached, but available for their own individual strings. So we have different strings for different notes on the piano, and everything is controlled by the key on a keyboard. So each note, each key on the keyboard is attached to a different hammer inside the piano. Let's have Nikita explain it a little bit further.
Guys, this is a piano if you can tell, and you just play by pressing down on the keys. Down here we have 3 pedals that manipulate sound as well. This is a sustain, this is a mute, this is the una corda, and una corda isn't really obvious because it just takes off the edge of the sound. When you play a scale on a piano, because it's an equal temperament instrument, you can't really change the pitch. Like each of the notes have its own like pitch that's associated with it that can't change unless you open this top box over here and you tune each individual note to get tighter and higher up here and looser and lower down here. So basically when you're playing it, there's no way to change the pitch as you're playing. To make it louder, you just press harder. To make it softer, you just don't press as hard. And yeah, I think that's it.
Thanks, Nikita. While we're in the mood for, hitting things with hammers of various kinds, that is pretty much what percussion is. And I can hit things. You probably are aware of hitting drums. You may not know, though, that just like the way strings can vibrate in different modes, so can two-dimensional surfaces. So this is another one of my favorite instruments, this kitchen spatula, and it has a two-dimensional surface, mostly really vibrating in one dimension, but it has a really nice sound. That's one. Another two-dimensional surface would be like the window in my Studio B. Finally, the other more common device would be a drum, right? So this drum has a bigger and smaller. You might guess that the vibrations on this will produce longer wavelengths and make lower notes. Let's find out. So there we go. That did what we thought it would. Let's take this up a bit in scale. We have Miles on the timpani. He's going to show us how the timpani works.
These are the timpanis. It's basically just a big tuned drum, and you change the pitch with these pedals on the bottom. And each one has a different
Hey, Miles is also the creator of an awesome slow motion video of a bass drum being hit. He shot this at 1,000 frames per second. We'll play it back at 30 frames per second, so you'll see it in very slow motion. take a look at this. See if you can see the vibrations of the drum head as it's being hit. That's a great video. Thanks, Miles. I appreciate that. So let's see. I think that just about wraps it up for today. I would say in review, we've seen the, oscillating air columns, and we've seen vibrating strings, and we've seen percussion instruments being hit. And these are all the essential elements of making music. So finally, let's see, a big shout out to the people who played their instruments here in this video. I will remind you who they are. That's Christine and Liam and Richa, Alpana, Ivan, Nikita, and Miles. And I'd also like to give a special thank you to you, Stuart, wherever you may be, for making such delicious black cherry soda. I'm Mr. Posh, and until next time, I'll leave you with this one final wave. See you later.